Good morning. My name is Tulio, and I'm going to give a brief introduction to density functional theory. First, I will introduce one of the problems that led to the construction of the theoretical framework of density functional theory. Then I will talk about what the DFT is and its main ideas and how it is implemented computationally. And final, I will comment on the difficulties and present some software that implement it. Well, to describe a system composed of several atoms, we regularly start from the Schrödinger equation, which we can separate into table part and the spatial part. The time part is easily solved, resulting that exponential with negative argument that depends on energy and time. The spatial part, which you are looking at here, which is also called the time independent Schrödinger equation, is not so simple to solve in most cases. The Hamiltonian is composed of kinetic energy of the electrons, the kinetic energy of the nuclei, the electron-electron interaction potential, the electron-nucleus interaction potential, and the nucleus-nucleus interaction potential. We know that the mass of the electrons is much smaller than the mass of the atomic nuclei. So the electrons respond quickly to the motion of the nuclei. So they adjust to the lower energy state almost instantaneously. So this problem will be approached so that the nuclei are at rest. That is, the kinetic energy of the nuclei is zero. Thus, the electron-nucleus interaction potential acts as an external potential. Uh, in this way, the Schrödinger equation can be decoupled and the partial relation to the electrons becomes as right in the question 9. We have already made some approximation, but is it now possible to solve any problem with countless atoms? Let's try to make some estimates. For each electrons in system, we have 3 degrees of freedom. So for n electrons, we need 3 n-wave functions. Assuming 100 points per coordinate and allocating 80 bytes for memory per point, the total memory allocation will be 80 multiplied by 100 to the power of 3n. The memory required just to store this data will be about 80 megabytes for one electron system, which is a good result because we could easily manage with the existing storage capacity. For system with 2 electrons now, you will need 80 terabytes just to store the wave function data. With some good symmetry relationships, one could reduce this, but it would already have a much higher memory cost than in the case of one electron. But it is still plausible according to the most modern storage devices. Now, as the number of electrons grows, the memory cost advances to surreal levels, making this kind of calculation impossible. If for 5 and 10 electrons, we would already have the need for this amount of the memory. Imagine for a carbon dioxide molecule, for example, 22 electrons, or even a gold nanocluster, which has more than 8,000 electrons. Therefore, other approaches are needed to solve the many water problems. And one of the options we have today is what we call density functional theory, or DFT. which we'll talk a little more about now. The density functional theory arose due to search for the replacement of the wave function by another physical quantity that would be as representative and descriptive as the wave function, but of an easier interpretation when simply natured, since the wave function is a vector defined in a complex space of arbitrary dimension. This physical quantity is the electron density, a function with direct physical interpretation and dependent on only three spatial variables. This simplification allows the use of DFT for systems with a very large number of electrons. Uh, in 1964, the paper published by Hohenberg and Kohn showed that the electron density can indeed be used as a fundamental quantity for the complete description of a system of interacting electrons, and therefore answered this question by proving these theorems. The first theorem enunciates electronic density for a ground state with a univocal function of the external potential. The second theorem tells us that energy calculated for any electron's density other than the ground state density will always be greater than the energy of the ground state. Then, through the minimization process for energy as a function of electron density, only the true electron density will be found as a minimum for energy. DFT implementation now. For the implementation of DFT, we have the formalism proposed by Kohn and Sham, which is a way to describe the electron orbitals using the density functional. The main idea of this formalism is to move from many body problems to a non-interacting particle problem, considering that the electron density of interaction particles can be obtained from the density of non-interaction particles. Therefore, it is done by properly separate the exchange and correlation term, which takes into account the many more effects, which is VXC.
2 minutes.
Okay. Then, given the correlation exchange term, we propose an electron density ρ, and we construct the effective potential V. Then we determine the constant orbitals with the resolution of the Schrödinger equation, which will give us a new electron density. With this, we compare this new density with the density initially proposed, and if the convergence criterion is met, we have a desired electron density, and not if the circle begins again using a mystery between the two densities to front density and to be used in the next step. So apparently we have all the tools to completely describe the size system. In fact, the correlation and exchange term is not so easy to obtain. Perhaps determining the expression of the correlation exchange energy term is the biggest challenge of this theory. Here I show two examples of the analytical approximation for exchange and correlation functionals, which are LDA, local density approximation, as it takes into account that the energy in a given region is constant and has terms that explicitly involve the electron density functional. And GGA, which stands for General Gradient Approximation, most often used in a strongly correlated system, and takes into account the gradient of the electron density functional. Finally, I show some software that implements the FT and allows the use of these theoretical tools. Some of them are open source, for example, Quanto Expresso. Well, this is a short summary of general ideas of the FT. I thank you for attention.